Hello everyone, this presentation examines the Carlsbad, New Mexico pipeline rupture, one of the most serious gas transmission failures in United States history. Natural gas pipelines form the backbone of the U.S. energy infrastructure, transporting over one-fourth of the nation's total energy supply. Because of their critical role, any failure can have devastating technical, environmental, and social consequences. Using the Carlsbad case, I will highlight how internal corrosion, management failures, and weak safety culture converge to cause both human tragedy and regulatory transformation. To begin with, let's look at what actually happened in Carlsbad site. The incident occurred when a 30-inch natural gas pipeline ruptured near the Pecos River in New Mexico. The escaping gas ignited instantly, producing a massive fireball that burned for nearly an hour and tragically killed 12 people who were camping nearby. The force of the rupture was enormous. It created a large crater along the pipeline, and a 49-foot section of the pipe was ejected in some pieces. Subsequent investigation determined that the rupture was caused by severe internal corrosion, a preventable failure that revealed deep systemic and organizational weaknesses. So, as mentioned, the Carlsbad failure was driven by internal corrosion, specifically a type known as microbiologically influenced corrosion, or MIC. In any form, MIC begins with the formation of a biofilm on the metal surface. This process, driven by microbial activity, represents a type of biodeterioration that can severely reduce the reliability and service life of buried pipelines. In the Carlsbad case, stagnant fluids inside the pipeline created ideal conditions for microbial growth. Combined with high chloride concentrations and dissolved oxygen, these microorganisms produced localized deep pitting that went undetected because of limited inspection access. The dominant organisms were sulfate-reducing bacteria known as SRB. As illustrated in this schematic, SRB use elemental iron from the pipeline as an energy source at the anode, while sulfate acts as the terminal electron acceptor at the cathode, a biochemical process that accelerates metal loss and causes corrosion. Beyond the immediate explosion, the Carlsbad rupture caused severe and lasting environmental damage. The intense fire destroyed vegetation and wildlife along both sides of the Pecos River, and the heat damaged nearby infrastructure, including bridges and pipelines. The incident also created a potential for soil and water contamination. Combustion and heat likely volatilized hydrocarbons and corrosive residue inside the pipeline, which could have leached into surrounding soil or waterways. Importantly, the victims were members of local community, a reminder that pipeline disasters often impact those with the least resources and political voice. This raises critical questions about environmental justice and how the risks of energy infrastructure are distributed among different populations. Corrosion control plays a vital role in preventing failures. That is obvious. However, the methods we use also have their own environmental footprint. First case is pigging. It's generally the most sustainable method because it physically removes deposits and water without relying on chemicals. However, smart pigging systems reduce waste and limit worker exposure to hazardous substances like hydrogen sulfide. Second one is coating. It's effective for external corrosion, but can introduce environmental challenges. Some older coatings contain volatile organic compounds or heavy metals, while modern waterborne and bio-based coatings are being developed to minimize toxicity and reduce life cycle impacts. The last one is inhibitors. It's another key defense against internal corrosion. However, many traditional inhibitors, such as chromates and phosphates, are toxic to both humans and aquatic life. Recent research focuses on biodegradable, non-toxic alternatives that releases active agents only when needed. The financial impact of Carlsbad disaster extended far beyond the immediate repair costs. Direct expenses exceeded $1 million, including pipeline replacement, bridge reconstruction, and site cleanup. However, indirect costs were far greater, including lawsuits, federal fines, loss of revenue, and lasting reputational damage. The company also faced a proposed civil penalty of $2.5 million from federal regulators. However, the real consequence was the loss of public trust and the realization that existing safety oversight was inadequate. In response, the U.S. government passed the Pipeline Safety Improvement Act of 2002, which marked a turning point in national policy. It introduced a shift from simple regulatory compliance to a risk-based integrity management approach, requiring operators to actively identify, monitor, and mitigate risks before failure occurs. Well, to wrap it up, the Carlsbad incident exposed critical technical and organizational weaknesses. The absence of an effective internal corrosion control program meant that early signs of corrosion went unnoticed, revealing shortcomings not only in engineering design, but also in operational oversight and maintenance practices. These weaknesses underscore the importance of proactive monitoring and integrated approach to asset integrity. At the same time, the tragedy highlighted significant regulatory gaps. The aftermath of Carlsbad prompted major regulatory reforms and reinforced the need for continuous improvement in safety standards, inspection method, and industry oversight. Together, these lessons remind us that preventing such incidents depends on both technical practices and a robust regulatory framework that evolves with emerging risks. This is the end of presentation. Thanks for listening.